Hello, welcome back. In the previous session, we discussed about some theory behind the design of reinforced beam. Let us solve a problem in this class. Please write down the problem. Design a balanced singly reinforced concrete beam section for an applied moment of 60 kilonewton meter. Use M20 concrete and Fe 415 steel. So this is the problem given. So if I read the problem, design a balanced singly reinforced concrete beam section for an applied moment of 60 kilonewton meter. Use M20 concrete and Fe 415 steel. And there is one more point, the width is limited to 175 millimeter. The width is limited to 175 millimeter. So as we discussed in the previous session, so in the design what we do, we are going to find out what are the dimensions required for the beam, that is breadth and depth, and also the steel required. So in this case, they have given the breadth 175 millimeter, that is fixed and we cannot change it. And another thing we need to find out is D. And the other thing we need to find out is AST, that is the area of tension steel. We don't have to calculate ASC, that is area of compression steel, because this is a singly reinforced section. And the problem says design a balanced section. So what is the meaning of a balanced section? If you open page number 67 and 68 of the code book, 68 and 69 of the code book, please open it. See, under 68, it says 38, limit state of collapse flexure. That is section 38, limit state of collapse flexure. And under 38.1, it is given some assumptions. And we are not going to discuss all the assumptions. Instead, we are going to discuss the assumptions B and F. So if you look at B, it says the maximum strain in concrete at the outermost compression fiber is taken as 0.0035 in bending. And when it comes to F, point number F, it says the maximum strain in the tension reinforcement in this section at failure shall not be less than, it is key, shall not be less than Fy divided by 1.15 E plus 0.002. So with these two things in mind, we can define what is a balanced section. See, a balanced section is one wherein both concrete and steel reach their limiting strain values simultaneously. So what it means? In the compression zone, concrete will reach its limiting value or limiting strain of 0.0035 and the steel will reach a value of Fy divided by 1.15 Es plus 0.002. That is a balance section. Okay. And we are supposed to design a balance section only for flexure. We are not worried about the shear because we don't have enough data to worry about the shear. Okay. So let us write what is given here. It is design a balanced singly reinforced concrete beam section for an applied moment of 60 kilonewton meter. So applied moment M equal to 60 kilonewton meter. Okay. So use M20 concrete. For M20 concrete, FCK is 20 Newton per millimeter square. And for Fe 415 steel, Fy value equal to 415 Newton per millimeter square. And the width of the beam is given as 175 millimeter. So what we need to find out? We need to find out the effective depth and the area of tension steel. We need to find out these two things. So before proceeding, look here, for an applied moment of 60 kilonewton meter. So what it means is this moment is calculated based on the service load. Okay. And when we are designing in limit state design, we are not supposed to use this value. Instead, what we must use is the design load. Okay. Design load, factored load or ultimate load. If they say it, it means the same. Okay. When they directly give that value, that is the design load or ultimate load or factored load, so then you don't have to multiply that value by 1.5. But here, because whatever is given as applied load, that is, applied moment, that is the service moment. That means again that is calculated based on the service load. To arrive at the design moment, we have to multiply this value by a factor called the partial safety factor for load, or simply it is called as load factor. So if you open page number 68, table 18, page number 68, table 18. So if you look at the table, leftmost column, it says DL plus IL. DL is nothing but dead load. IL stands for imposed load. Imposed load is nothing but live load. Imposed load and live load are one and the same. So just next DL plus WL, that is dead load plus wind load. We are not worried about the wind load. We are only concentrating on dead load and imposed load. So if you come horizontally along that line, you see 1.5. Okay, that is limit state of collapse. So this is limit state of collapse in flexure. Okay, so for dead load and live load. So the factor should be used equal to 1.5. Okay, so here for this moment, to arrive at the design moment, I am going to multiply this value by 1.5. Therefore, design moment or ultimate moment or factored moment MUD equal to gamma F multiplied by M value. So gamma F is 1.5, M value is 60, therefore MUD equal to 90 kilonewton meter. So where did we get this 1.5? That is from table 18, page 68. Page 68. So this is the design moment. So to start with, what we are going to concentrate is, we are going to find out what is the effective depth required. So to calculate the effective depth required. Effective depth D required. So because it is a limiting or balance section, so whatever the corresponding moment should be mu limit. So we are going to make use of the formula for mu limit, which is given under Annex G, G 1.1c. Okay. Please open page number 96. If you open page number 96, so for a balance section from Annex G, G 1.1c, page 96. See, if you are writing an examination, so you don't have to write all these things. No need. You can directly start solving the problem by picking up the appropriate formulas from the code book. Okay, I'm only writing this for your reference, nothing else. So from there, I write mu limit equal to 0.36 xu max by D, 1 minus 0.42 xu max by D, BD square FCK. So the formula is given there. Okay. So in this case, for a balance section and for Fe 415 steel, and for a balance section, xu max by D should be equal to 0.48. Where did you get this value from? If you open 38.1 on page 70. So I am going to open, please open it for a moment and look where exactly it is located. This corresponds to 38.1, page 70. For Fe 415 steel, the value of xu max by D equal to 0.48. Okay. This is 38.1, page 70 of the code book. Okay. So by substituting the value of xu max by D equal to 0.48, and one more thing, in case of mu limit, we are going to substitute the value of MUD. Okay? And by substituting MUD for mu limit, we get, so in place of mu limit, I am going to substitute these values. This value 90, and I am going to convert this value into Newton millimeter, that is 10 to the power of 6, 0.36, and xu max by D is 0.48 for Fe 415 steel for a balance section, 0.48, 1 minus 0.42 into 0.36, and B is, see here, B is restricted to 175 millimeter. Okay. So that is B equal to 175 millimeter. And D we don't know, that's what we are trying to find out. And the FCK is 20 for M20 concrete. Okay. And after simplification, I am going to get 480 D square MU limit 10 to the power of 6 equal to 482.87 into D square. Okay. Therefore, D equal to 432 millimeter. This is the depth, that is the effective depth, not the overall depth I am talking. This is the effective depth required for a balance section. Once that is done, we need to find out what is the area of steel required for the balance section. So to calculate, the area of tension steel AST, to calculate the area of tension steel AST. So by equating total compression to total tension, we get XU by D equal to 0.87 Fy AST divided by 0.36 FCK B D. So just if you cancel this and this, D and D here, and if you cross multiply this with XU, so 0.36 FCK XU multiplied by B will give you the total compression force. So for force equilibrium, that should be equal to total tensile force in the steel in the tension zone. So this is the total, this with XU is the total compressive force in the concrete in the compression zone, and this is the total tensile force in the steel, of course in the tension zone. So by equating and just dividing both sides by D, we are going to get this. So this formula is available in Annex G under G1-1A, page 96. Okay. So for a balance section, XU by D becomes XU max by D, and AST becomes AST limit. Okay. So by substituting the values of this and this here, so when you substitute the value of XU max by D in this place, which is 0.48, look here, XU max by D is 0.48, substitute, and this is known, and these values are known, D is also known, and we can get AST, that is nothing but AST limit. Okay. So by substituting, the values in the above equation, we get, so in place of xu by d, I am going to substitute xu max by d. So for a balanced section with Fe 400, xu max by d equal to 0.48. So I am going to substitute 0.48, that is equal to 0.87 Fy steel, that is 415, into AST becomes AST limit divided by 0.36 multiplied by M20 concrete. So FCK is 20. B is given 175 and D is 432. That is the area, that is the effective depth for a balanced section which we calculated just now. So by substituting all the values, we are going to get the value of steel, that is AST limit. Therefore, AST limit equal to 724 millimeter square. This is the area of steel required for a balanced section. So what it means, if we take a rectangular section of width 175 millimeter and effective depth 432 millimeter, not the overall depth, effective depth, and provide the reinforcement of this much area exactly, then the section is going to be balanced. Okay? But in reality, it is almost impossible to achieve a balanced section. Okay? It is almost impossible to achieve a balanced section. Just to give an example, for example, here, so this is 724 millimeter square. So let me assume we are providing 16 millimeter dia bars. Okay. So when you are providing 16 millimeter dia bars, we need to find out how many bars we need. So for that, what we do is we are going to divide this value by area of each bar, pi by 4, 16 square. Okay. So this comes to around 3.5 nearly, but we cannot provide 3.5 bars. So we can only provide 4 bars. Once you provide 4 bars, it is going to be 804 millimeter square, which is greater than this. Then the section will be out of balance. It will not be a balanced section. Okay. So theoretically, yes, these are the values for a balanced section. And it is recommended that we have to design a section as under reinforced always. Okay. When we say under reinforced, it does not mean that we have to provide less reinforcement. Please keep in mind, we are not providing less than what is really required. Okay, what is the meaning of under reinforced or over reinforced or a balanced section? As I said, a balanced section is one wherein concrete and steel reach their respective limiting strain values simultaneously. That means concrete reaches its limiting strain value of 0.0035 at the same time as the tensile steel reaches its limiting strain value of how much? Fy divided by 1.15 Es plus 0.002 as given in the code book. Okay, on page 69 under assumption B and F. Assumption B and assumption F. Okay, that is a balanced section. So when we are designing, and we should not design the section as an over-reinforced section, that is not recommended, because if you look at the code on page 96, under G 1.1, point D, if XU by D is greater than the limiting value, the section should be redesigned. See, if XU by D is greater than the limiting value, means the section is over-reinforced. Then we have to go and redesign the section. So what is the other option we have? We cannot design a section as a balanced section, and also we are not supposed to design a section as an over-reinforced section. The other option is under-reinforced. As I said, just because I say under-reinforced, it does not mean that we are going to provide less steel. Instead, we are going to provide the steel required according to the design. But in case of under-reinforced section, what happens is, when you subject a beam to load until failure, okay, in case of under-reinforced section, we have provided concrete, okay, and steel in such a proportion that the steel will reach its limiting strain value of Fy divided by 1.15 Es plus 0.002 first, before concrete reaches its limiting strain value of 0.0035. Okay. Once the steel reaches its limiting strain value, not the limiting strain value, that is the yield strain value, then the concrete is not, steel is not going to fail suddenly, because steel is ductile. It keeps elongating. That means strain keeps on increasing beyond the value of Fy divided by 1.15 Es plus 0.002. As the strain increases in steel, correspondingly the concrete strain will increase. Once the concrete strain reaches 0.0035, then the failure happens. Because here failure is defined by the strain in concrete, which is equal to 0.0035. Okay. So why we prefer under-reinforced section? Because before failure in an under-reinforced section, because of elastic or ductile property of steel, it gives enough warning. Okay. So what if you design a section as over-reinforced? That means if you provide steel more than required for a balanced section, that is, it is going to be over-reinforced. In such cases, when you keep loading a beam, the steel will not reach its strain value of Fy divided by 1.15 Es plus 0.002 first. No. The strain value will be within its yield strain value. But concrete reaches its value of 0.0035. Once it reaches, the concrete fades first. When the concrete fades first, it does not give enough warning. The failure is going to be sudden. Okay? It fades without giving any warning. So it is recommended that whenever you design a section, you always design the section as under-reinforced. Don't ever think that under-reinforced is a section wherein we are going to provide less reinforcement. It is not so. Okay? We are going to give enough reinforcement. Okay? The only thing is the strain in steel reaches, it will reach its yield strain first before the concrete reaches. That gives enough warning. Is it clear to you? So with this, we will go to the next problem. Problem number 2. Meantime, you write down this. Find the reinforcement find the reinforcement for the beam of the above example. For the beam of the above example, for the beam of the above example, if the effective depth of the beam is kept equal to 500 millimeter. Okay. See, if you take a beam section with some reinforcement and the neutral axis comes somewhere here, and this is called as the depth of the neutral axis xu, and this is the effective depth of the beam section. So, if you draw stress variation diagram in steel and concrete, when the limit state is reached, and this is going to be the compressive force and this is going to be the tensile force. Okay. So, that is 0.87 FYAST. Okay. So, I am not going to write this value, I am going to keep this as T. Okay. So, centroid of this area is going to be the centroid of the compressive force, and this is the lever arm A, and this force and this force are equal. Compression force equal to tensile force to maintain force equilibrium. Because these two forces are separated by a distance of A called the lever arm, these two forces form a couple of magnitude CA or TA, T multiplied by A or C multiplied by A. Okay. And this couple, that is the moment, this moment is going to resist the moment caused due to the external load. Okay. So, in the previous example, if you remember, for a balanced section, the effective depth required is 432 millimeter. For a balanced section, that is 432 millimeter. And when this is D, this is going to be 0.42 XU. So, lever arm is D minus 0.42 XU. Is it not? So, to take care of the moment of 60 kilonewton meter service moment, and the ultimate moment is 90 kilonewton meter. So, what if we increase this moment? Okay, this moment is good enough to take care of this external moment to the load. So, this T is, say I take this T multiplied by A equal to 90 kilonewton meter. Okay. So, this is say 0.87 FYAST. and the lever arm is D minus 0.428 equal to 90 multiplied by 10 to the power of 6. Okay. So, AST equal to 90 10 to the power of 6 divided by 0.87 Fy D minus 0.42A. So, 42XU, sorry, 42XU. Okay, this is for a balanced section. If you calculate the area of steel, it is going to be 742 millimeters square. So, that is what we calculated. So, in this case, what the problem says is, for the same moment, we are not changing the moment is the same. The beam section has been increased, that is the D value, from 432 to 500 millimeter. Okay. So, if you look here, so to counteract the moment, we need area of steel and also the lever arm. This is the lever arm. So, in this case, when you increase the depth, this value will increase. Once this value increases, the area of steel required will be less than what is required for a balanced section. The section becomes under reinforced. So, you need less area, but that less area of steel is good enough to take care of this moment. Okay, we need to find out what is the area of steel required. So, I repeat, once you increase the depth to 500 millimeter, that is the effective depth to 500 millimeter. From the previous example, for a balanced section, we need D equal to 432 millimeter. In this case, it is 500 millimeter. Automatically, the section becomes under reinforced. Okay. So, once it becomes under reinforced, the formula we are going to make use of is G 1.1b under annexure G on page 96. Okay. With this, let us proceed. In the above example, we got area of tension steel AST equal to 432 millimeter, 742 millimeter, 724 millimeter, okay, and D equal to 432 millimeter for a balanced section. If we increase the depth, above 432 millimeter for resisting the same moment, the section becomes under reinforced. The section becomes under reinforced. So, for an under reinforced section, for an under reinforced section. So as given in the code book, mu equal to 0.87 Fy ASTD 1 minus 0.87 Fy AST divided by BD FCK. This is from G1-1B, page 96. So by substituting the values, in the above equation, we get, for mu value, we are going to substitute MUD, that is 90 multiplied by 10 to the power of 6, that is equal to 0.87 into 415 multiplied by AST, that is what we are trying to find out here, and D is 500 millimeter. Okay. One minus 0.87, 415 into AST divided by B is 175, D is 500 into FCK, that is equal to 20. Okay. Next, after simplification, we are going to get AST square minus 4216.9 AST plus 2.102 into 10 to the power of 6, that should be equal to, that is equal to 0. So therefore, AST equal to 577.6 millimeter square. Therefore, area of steel required equal to is AST 577.6 millimeter square. Look at the value. In the previous case, for a balanced section, the area of steel required was 724 millimeter square. Once we increase the depth, what is the area of steel required? 577.6 millimeter square. Okay. So even though when we are solving a design problem, we try to approach for a balanced section, it is even recommended that, keeping in the mind the economy, we have to design an under reinforced section, not even a balanced section. Because a balanced section always gives the least area of concrete and the maximum area of steel. But when it comes to the price, so steel is relatively higher in price, in price when compared to concrete. So we have to concentrate on this one, saving steel at the cost of concrete. So that can be achieved only by going into an under reinforced section. Okay. So I hope this is clear to you, and we are going to take up one more example in a detailed way. So in the next example, we are going to take care of flexure, shear and deflection. Okay. Thank you.